So, shall I start?
Are we ready? So I'm the chair, so let me. Well, the Prospectus. Just to go over the procedures here, if you haven't Prospectus before. There's going to be a 35-minute talk by is it Shantanu? Is that my
Yes.
name right? Shantanu. And that will be followed by open questions from anybody, and then after the open question period, we'll have everybody except the committee lead, and then we do a closed session with just the committee, and then we talk without the candidate, and then we deliberate and then make a decision. So yeah, I think that's about it. Kayhan, maybe you could introduce.
So this is Shantanu.
Yeah.
He has been in our lab since 2021. He was only a bug. So some of the small group of the students that moved with me from University of Pittsburgh has been working on this problem about intersection of robustness and machine learning, identifying issues with black box, all in the context of vision. He has been very instrumental in working in our collaboration with Clare on breast cancer project. So looking forward to that.
Yep. Thank you, Kayhan. Hi, all. Welcome to my Prospectus defense. Myself, Shantanu, and I'm a fifth-year PhD student under the supervision of Dr. Kayhan Batmanghelich. So the goal of my thesis is to detect systematic mistakes encoded in a pre-trained black box. Why should we do that? We need to detect the systematic mistakes to design better mitigation strategies, collecting more data, changes in the model architecture, or training strategies to increase robustness. So here's the most important thing is to understand what is a systematic mistakes. So let's first decode it. So systematic mistakes are the model errors where we see a particular pattern. Let me explain you with this famous waterbirds dataset from computer vision. So this is a particular dataset where the images of birds have been superimposed with the corresponding background. So the water birds are correlated with the water background and the land birds are correlated with the land background. Any classifier which will gonna be trained in this particular data will gonna have disparate performance among these 4 subgroups. So you can see that the accuracy of water bird on land is around 69%, whereas accuracy of water bird on water is 94.2%. It is because the classifier is using the background information to classify the images of birds. Here, the classifier is making systematic mistakes on the subgroups which are not correlated with the label. This particular phenomena is very prevalent in medical imaging as well. In chest X-rays, pneumothorax is a disease where chest tubes are inserted to patients to maintain the lung pressure. So most of the pneumothorax patients have chest tube inserted in them. Now an AI model may equate the presence of chest tube with pneumothorax on chest X-rays. As a result, the performance of pneumothorax patients on chest tube is often higher than its performance on the pneumothorax patients without chest tube. Here, the model is making systematic mistakes on pneumothorax patients without chest tube. Now, the question is, how can we detect the mistakes from a trained model? We know that a trained deep learning model is often known as black box. In the first aim, we leverage a concept bank and carve out a mixture of interpretable models out of the black box. Now, the question is, what is a concept bank? A concept bank contains additional annotations of high-level attributes or human understandable features. For example, for the birds dataset, some of the concepts in the concept bank may include wing color, breast color, or tail pattern. However, the concept bank is expensive to get. Also, if the goal is to explain the errors, then explain the whole black box is too much. So we relax the assumption of having predefined concept bank and use free-form text in the form of captions or radiology report to debug the model. We can see that the captions or the report, they encode a lot of signals for visual errors. For example, on the right, we can see that radiology report consistently mentions chest tube for pneumothorax patients. So here is what we do for AIM2 and AIM3. In AIM2 and 3, instead of relying a predefined concept bank, we're going to use a free-form text and project the representation of the classifier to the vision language space and detect the subgroups where the model is making consistently mistakes. Specifically, for AIM2, we're going to develop a vision language model for mammography to detect breast cancer. But why do we focus on breast cancer? Because breast cancer is the most common form of cancer worldwide. In 2022 alone, it accounted for 2.3 million new cases, along with 650,000 new deaths. Detecting it early makes a significant difference, as the studies show that early screening at the age of 40 can reduce the death of breast cancer by 25%. However, early detection comes up with a lot of challenges. First, it carries a lot of risk of overdiagnosis, which means that many patients has to go through unnecessary surgeries, radiation, and hormonal therapy. Especially in the US, new guidelines now recommend screening should be started at the age of 40. It means that many more patients without symptoms will have to go through the diagnostic process. This will gonna put a lot of load to our radiologists who are already overworked. Nearly half of their days have been spent through communications and documentation, which leads to fatigue and can increase the risk of diagnostic errors. So, and finally, in AIM3, we're going to develop the method to debug the model with the help of language. Let's go through each AIM one by one. So let's first dive deep on AIM1, where we're going to extract a mixture of interpretable models out of the black box post-hoc using first-order logic. So let's first decode why we need post-hoc, first-order logic, or FOL, and interpretable models. We need post-hoc models because it will not gonna alter the black box. So the performance of the black box remains unchanged. However, it does not support any intervention. Now, why interpretable models? Because they support intervention. Now, what do I mean by intervention? Let me explain with the help of concept bottleneck models, which is a special class of interpretable models. Here, the model misclassifies this particular image as wrongly as Brewer Blackbird. Along with the prediction, concept bottleneck models also highlights the top concepts along with the top values, which are important for the downstream prediction. We can intervene on the concept values by using an oracle and alter the decision to the correct prediction. In literature, this is called test time intervention. Finally, why first order logic? First order logic are interpretable rules. The left-hand side of the first order logic generally consists of the labels. In medical imaging, it consists of the disease labels. The right-hand side denotes how the concepts are related to each other for the class label. These first-order logics are composed of the clinical rules, which often are invariant from one hospital to another. For example, the rule to detect cardiomegaly will gonna remain unchanged from one hospital to another. So if we learn these rules well, we can effectively transfer these models from one hospital to another. And also importantly, we can easily intervene on these rules to change the decision. Now let me explain you the setup. We assume that on the training data, we are given with the images at X's, the class labels as Y, and the human interpretable concepts as C. Also, we are given with a pre-trained black box. This particular black box was trained to predict the label from the image, and it did not use any of the human interpretable concepts during its training. The black box is decomposed into two different functions. One is phi, another one is h0. Phi is the feature extractor, which is composed of all the CNN layers in a convolution network. H0 is the linear layer on top of it. For medical images, we are not given with the predefined concept bank. Instead of that, we are given with a radiology report. With the help of a parser named radgraph, we first parse this radiology report and get the human interpretable concepts. And finally, this is the triplet that we get. we get X as the image, C as the concept, and Y as the label. Remember that we start off with a black box. The idea is that the black box often encodes the human interpretable concepts in its intermediate layers. So the first step is to discover those concepts. How we do that? We take the representation from the feature space to the concept space. For this, we learn a linear projector T, which learns this mapping from phi to the concept space. This linear projector T will gonna give us the probability of the concept being present. Here, these concepts are shown in using these toggle bars, which shows the presence and absence of these concepts. These probabilities will be the inputs to the downstream interpretable models. So what do we do when we discover those concepts? We try to find out a rule in the form of first order logic to combine the different concepts and mimic the behavior of the black box. On the right, we're gonna show that how this method will gonna work for this particular data set, which is CUP200, which is a bird classification data set. These rules are often very simple and they only work well on a very specific subset of data, and they are not generalizable for the entire data set. So we use a selector which selects between the black box and the corresponding interpretable model. These selectors are usually a linear classifier. It uses the interpretable model when it is confident. When it is not, it defers the decision to the black box. For each iteration, the selector always has a budget of 20%. So basically for each iteration, the corresponding interpretable model will gonna cover the 20% of the data. This interpretable model also was trained using knowledge distillation loss from the black box. So let me give you one example on the right. You can see that for the first iteration, the selector selects these two bird images and route it to the corresponding interpretable model. And the first interpretable model uses these two concepts to classify these two birds as olive-sided flycatcher. Whatever is remained, we refer to them as residual. We copy the initial feature extractor to the next phase and optimize the last layer of the neural network to specialize on the residual data. So if the first interpretable model covers 20%, then this residual will gonna cover 80% of the data. Thus, this residual will gonna become the black box for the next iteration. On the right, the first two images have been covered by the first interpretable model. So this residual will gonna cover these remaining 4 images. And we're gonna continue this process. At the end, we're gonna get these 3 interpretable models and which have been extracted during the different phases of the training process. We call them experts because they specialize on specific subsets of data. And finally, there could be some residual left, which will not gonna be explained by any of these interpretable models, and this will be the unexplainable part of the data. On the right, you can see that this particular bird has not been covered by any of the interpretable models. So this is the unexplained part of the data. Next, we show experiments that our method will not gonna compromise on the accuracy, and also we're gonna do effective transfer learning. So here, remember, we don't want to compromise the performance, and this particular experiment will show that. Here, we aim to extract the mixture of interpretable models out of a vision transformer for CUP200 dataset. We compare our method to two state-of-the-art concept bottleneck models at that time. One is the basic concept bottleneck model, and another one is the post-hoc concept bottleneck model. You can see that the black box achieves an accuracy of 92%, whereas our model, which covers 95% of the data, achieves an accuracy of around 90%, which is 2% less than the black box. Also, it outperforms significantly the remaining baselines. The result is consistent for the CNN as well. We can see that the performance gap between the black box and our method is minimum compared to the baselines. This is because our method uses various experts which specialize on specific parts of the data compared to the baselines, which uses one interpretable model and hope that interpretable model will gonna do well for the entire data set. Let me give you some rules that we extracted for Mimic CXR dataset as well. Suppose during the inference time, these 4 images come to our model. You can see that first expert uses these 2 concepts, right apical lung and right lung unspec, to classify the first 2 images as pneumothorax. Whereas expert 2 uses emphysema and left lung unspec to classify the 4th image as pneumothorax. And finally, the expert 3 uses left apical lung to classify the third image as pneumothorax. You can see that specific expert classifies specific images using specific concepts. So our method focuses on discovering local concepts, which are important for that group only. Okay, so we are able to get the set of interpretable models out of the black box. Now, what is its application? We apply it to do effective transfer learning. Consider this particular setup where we are given mimic CXR dataset, which is based in Boston, and we trained a black box to classify the chest X-ray image to pneumothorax, and we aim to transfer this black box to Stanford CXR. So the gold standard is transfer learning, where we use the training data from the target site to classify the image to pneumothorax, and we update the entire black box. This method is data and computationally inefficient because we are relying on the large data. We are relying on the large training data of the target site, and also the entire black box will be updated. However, the clinical rules that we learned in the last slide, they are invariant. So the experts, they learn those clinical rules, which will not gonna get changed from one hospital to another. We can effectively transfer them to the target site with limited data. So here is some result. We aim to transfer the black box trained on Mimic CXR and transfer it to Stanford CXR. X-axis shows the different proportion of data available in the target site. We start off with 2.5% and we go all the way till 15%. The x-axis shows this proportion and the y-axis shows the AUROC. The gray one is the vanilla black box and the blue one is our method, the mixture of interpretable models. You can see that with much smaller amount of data, we achieve better performance. This is because our method focuses on concepts which remain invariant across hospitals compared to the data-hungry black box. The results are generalized to other diseases as well. So here is the conclusion from AIM 1. We extracted the mixture of interpretable models out of the black box. With them, we effectively transfer them to target sites with limited data. So in AIM 2, our goal is to develop the first vision language model for mammography. So let's dive deeper. Before that, let's motivate why we need SSL-based vision language model. Because VLMs learns to generalize features which perform well on variety of tasks. For example, here, BioMedClip is the state-of-the-art chest X-ray foundation model, and it does well on a variety of diseases shown in the x-axis. Also, VLMs not only do well on disease predictions, they can also predict the bias-inducing sensitive factors like age, sex, as shown in the literature. Here we can see that a VLM model, check0, outperformed the radiologist in predicting race from chest X-ray images. Also, we can see that it is useful to detect other sensitive attributes like race and age. Many of these factors cause systematic mistakes, so we can build robust VLMs for mammography and ultimately use it to detect the systematic mistakes from a trained black box in our next aim. One possible strategy to develop this VLM is to use the state-of-the-art generalist foundation models like MedGemma from Google, or fine-tune a chest X-ray foundation model pre-trained on a large imaging dataset. The idea is that the extensive pre-training could lead to better image-text alignment. However, this is not always the case, because generalist models, they often work on low resolution or downsampled images, so they can miss the subtle but important features like microcalcification or architectural distortion, which are very important for breast cancer diagnosis. For example, MedGemma operates at a resolution of 896 by 896, and also models like DynoV3 and chest X-ray models, they use 224 by 224. This will gonna lead to lower data efficiency and weaker zero-shot performance. Also, we can take advantage of mammography report. They routinely include key prognostic details like calcification or breast density, which are known risk factors for breast cancer. We can train large-scale foundation models by aligning these clinical text with mammography images. It will help us to learn both diagnostic and prognostic features. So in this aim, we first propose MammoFM, which is pre-trained using screening mammograms. It has one image encoder and one text encoder. For each exam and for each breast, for each patient, we have two views. So these two views are two images, which are CC view and MLO view. We treat the CC view as the original image and the MLO view as the augmented image. If one view is missing, then we're gonna use the standard image augmentation to create the augmented image. Both the views will gonna be passed through the image encoder, which will gonna give us the image embeddings for the original image and the augmented image. For the text, we separate out the findings and the impression, and we're gonna send the impression and the findings section through the text encoder, which will gonna give us the text embedding for these two sections. Now, if one section is missing, then we're gonna use standard back translation. We're gonna translate the report from English to Italian and then back to English to create the augmented variant. Finally, we apply contrastive learning across all pairs: image, text, image and augmented text, augmented image, and text. Our pre-training data comes from a variety of sources. Some of them has one view missing, some of them has one particular section of a report missing, and this loss can handle everything. The image encoder here is efficient at B5, which handles large 1520 by 912 image resolution. The text encoder is modern BERT, which we first fine-tuned using 200K radiology chest X-ray images from University of Pittsburgh Medical Center. And ultimately, we use those weights to initialize the text encoder. We use a large corpora of training data sets collected from these four sites: Mayo Clinic, University of Pittsburgh, Boston University, and from Emory. Here, this is the summary statistics for them. Here, N denotes the number of patients. This slide shows the data efficiency of MammoFM evaluated on RSNA dataset on cancer classification. Remember, this particular dataset was not a part of the pre-training dataset. Here, we use a linear classifier on top of the MammoFM image encoder and fine-tune that end-to-end. The x-axis shows the percentage of training data used. We started from 10% and go all the way till 80%. The y-axis shows AUROC. Here, we compare our model to MedSigClip, which is a 400 million parameter model from Google, which serves as an image encoder for their MedGemma model. Remember, MedSigClip has 400 million parameter, whereas our MammoFM has only 30 million parameter. Still, you can see that MammoFM in blue consistently outperforms MedSigClip, even when it is trained with just a small fraction of data. This shows that MammoFM is highly data efficient, and its domain-specific pre-training and the multi-institutional diversity make the model far more effective than the generalist one. Yes.
That's not trained on mammogram data.
Yes.
Or fine-tuned mammogram data running.
No. But here, when we do this experiment, we actually fine-tuned it on mammogram itself. So here it is a complete fine-tuning experiment. We fine-tune both MedSigClip and MammoFM. The result is consistent for other dataset and other diseases as well. So in this aim, we learned robust mammography features for building the first vision language model for mammography. We did comprehensive experiments with many more dataset and tasks, which I skipped. It outperforms all the generalist industrial models to diagnose mammography-related features. We also apply this VLM to two of the most important applications in mammography. We use it to interpret the risk of a SOTA black box risk predictor. And also we use it to develop the first report generator in mammography. I'm not going through this part in details in the interest of time. I have the backup slides, which I can go over after my main presentation. Now we are going to aim 3. In aim 3, we develop a method which we're gonna use language or free text to detect systematic mistakes. How? First, we use the reports and captions for medical images and natural images respectively. Next, we use the vision language model. For natural images and chest X-ray, we have got plethora of options. For natural images, we can use CLIP. For CXRs or chest X-ray, we have Gloria, MedClip, CXR Clip, Convert, etc. For Mammo, there is a gap. We fill that gap with MammoFM from aim 2. And also an important note, we are not only interested in detecting visual systematic mistakes, we are also interested in detecting non-visual systematic mistakes. And a spoiler, we're going to use LLM for that. In medical imaging, we trace the non-visual mistakes from a wide variety of sources. They can arise from electronic health record, data pre-processing pipelines, and metadata including age, race, device setting, etc. These relationships are often hard to capture using pure visual techniques, and they often leave a trace in the form of language which you can send through LLM, which it will gonna use it to detect these mistakes. So first, let's understand how a human will detect the biases if he wants to do it. First, he sees a bunch of correct samples and a bunch of incorrect samples. Then he creates summary for the corrected ones and the incorrected ones. And then he comes up with some hypothesis which can be potential reason of the mistake. And finally, he will gonna test the hypothesis or validate the hypothesis by checking the performance gap. We're gonna basically do this entire thing automatically. So here we propose ladder to do that. We start off with a pre-trained classifier. The classifier is decomposed into the feature extractor phi and the linear head h. The classifiers classifies a bunch of samples correctly and a bunch of samples incorrectly. We project the representation of the feature extractor of the classifier to the vision language space. For this, we're gonna use a linear network to learn this projection. In the vision language space, we group them based on the correct and incorrect predictions. Next, we get the mean embedding of the correct and the incorrect ones and get the feature level difference, big delta. Next, we use captions or report. Based on the image embedding difference, big delta, we retrieve the top case sentences from the caption or the reports which have the highest similarity with delta. These are the sentences, they encode various visual concepts which drive the model error. We'll also leverage the rich metadata from DICOM headers. These non-visual concepts often correlate with data distribution shifts, very prevalent in medical imaging datasets. Next, we add patient-level data such as age, blood pressure from EHR record. These fields, when combined with imaging metadata, gives us a comprehensive view of context, enabling ladder to discover systematic mistakes which are clinical, not just visual. Finally, we send all these EHR record, the metadata, and the sentences to LLM. The job of the LLM is to come up with a set of hypotheses, the potential reason of mistakes. Finally, we cluster the images which are faithful to that particular hypothesis. For example, here we can see that one of the hypotheses that ladder selects is chest tube. And it is well aware in literature that a deep learning classifier often performs worse in the subgroup of pneumothorax without chest tubes. We validate that by comparing the performance gap of the classifier in presence and absence of the concept, that is the chest tube here. For this entire process, we use the held out data. Also for medical imaging data sets, we focus on positive samples. That is the patients with the disease. Here is an example of another hypothesis, fluid levels. Unlike the existing bias discovery method, our method does not use any labels for these hypotheses. We use prompts provided by LLMs to label these hypotheses. Okay, so here is the qualitative results from Waterbird's dataset classifying waterbird level. We know that waterbirds are often correlated with water background. So the first bias or the first hypothesis that ladder detects is docks and boats. This is quite consistent with the ground truth water background. We can see that the classifier attains 97% accuracy in presence of docks and boats compared to 69% accuracy when docks and boats are absent. Similarly, on medical imaging datasets, NIHC-XR ladder discovered the ground truth correlation chest tube for the disease pneumothorax. We can see that the classifier performs pretty well in presence of chest tube compared to the one when the chest tube is absent. And here is a comprehensive set of biases that ladder discovered for 6 datasets. Ladder can also detect non-visual biases. So for RSNA cancer dataset, it uses the metadata and discovers biases like age from EHR record. We can see disparate performance across young and older subgroups for breast cancer. This is consistent with the literature as younger patients often have denser breast density, which makes it hard for the classifier to detect the disease. Here is a comprehensive set of non-visual biases that ladder detects. Okay, so now from here on, I'm going to my proposal part. So suppose ladder detects these many hypotheses where the model makes systematic mistakes consistently. However, I'm arguing that it is not always the fault of the model. In my proposal, I argue that many of these errors will be explained by the data distribution shift, and we're going to reject many of these hypotheses. This will help us to focus on the actual biases of the model. So let's take a step back and abstract what ladder does. Ladder effectively calculates this particular metric. This one on the left is the performance of the subgroup. This is the raw subgroup performance for the subgroup A. Here A is a subgroup of interest. It can be either come from metadata or it can be one of the hypotheses proposed by ladder. This one is the average performance of the model on the particular class, say cancer patients. Here M denotes the metric of interest. It can be AUR, ROC, accuracy, recall, etc. R denotes the prediction from the model, and Y denotes the class label. Let's first draw the causal graph to understand the data distribution. We start off with the node M. Now X and Y are related to M because M is a function of R and Y. X is related through R because R is fx, which is a function of X. I'm not denoting another node here. But importantly, how X and Y are related. This is the direction. We assume that Y is causing X. Why? Because the pixels in the image depend on the disease labels. For example, chest X-ray image of a healthy patient is significantly different from an ill or an unhealthy patient. Next is A. There are two ways in which A can be related to either X or Y. One is this. Here, A is related via unobserved confounding. So the dotted lines denote the unobserved confounding and the solid arrows denote the causal direction. Here, A and X are conditionally independent of Y. In literature, this is known as label shift. Another way is A and X, they can be causally related to each other via unobserved confounding. In literature, it is known as presentation shift. So let me motivate you why we need to model this causally through this toy example. Suppose a deep model is predicting cancer from mammograms. This is the average model error on the cancer patients, which is 11%. On younger patients, the average model error is 29%. So the gap is significant, and we can conclude that the model is struggling on younger patients. However, I argue that the number does not tell the entire story. Also, this is how ladder detects the error, and also a bunch of almost all the literature in fairness, they also get into this kind of conclusion just seeing by these two numbers. Let's see how this number 11%, it actually comes from the population. If we dig deeper, there are 80% cancer patients which have fatty breast and 20% cancer patients have dense breast. And on the fatty breast, we assume that there are 5% model error. And on the dense breast, we assume that there are 35% model error. So cumulatively, the average model error comes as 11%. Similarly, let's see how this 29% model error comes. In the subgroup, say we have 20% fatty breast and 80% dense breast. This is the subgroup of the young patients. So the model error is 29%. And we already saw that the gap is significant. When we measure error, we only concentrate on these numbers, but we don't consider the internal mechanism of generating these two numbers. However, I argue that this comparison is not right. Why? because the distribution of density has changed in these two groups. We have to make these two distributions, the population distribution and the subgroup distribution, somehow similar to have apple-to-apple comparison. Now let me do a small calculation again. Let's choose this variable density. We saw that 80% young patients and 20% overall patients have dense breast. Let's calculate the weights in this red distribution. So what does this 4 means? The weight comes as 4. So what does this 4 means? Since dense tissue is common for younger patients but rare for the general population, we apply this 4 times weight for the population's disease cases. This forces the population density distribution to match the young group's distribution. Similarly, we can calculate the weights on the fatty breast, and if I do the math, the model error comes as 29%. And this matches with the model error for the subgroup. So what just happened? Basically, we created a pseudo population out of the general population of cancer patients. In the general population, we have more fatty breast compared to the dense breast, and it is reversed in the subgroup of young patients. So we created this pseudo population from the general population by upweighting the contribution of the patients of dense breast and vice versa. The pseudo population is a synthetic population which is statistically same as the young population. I'm denoting that pseudo population as V. It is often denoted as the control variable in causality. If I draw a causal graph, it looks like this. A is age, which is causing V. Here, V is density. We know that with more age, the breast becomes fatty. So A is causally influencing Y. Sorry, A is causally influencing V. And for fatty breast, it is easier for the model to diagnose cancer. So here, V is causing the prediction R. While creating the pseudo population, we are basically intervening on V to break this age. Basically, this step does this. What would have happened if the population distribution is same as the subgroup of interest? Now we can conclude that the model is struggling on dense breast, not the younger patients. In other words, we conclude that the performance disparity is mediated by breast density, rather than being a direct bias against the younger demography. Now I'll introduce some more notations here. So the one in the left is the raw model performance of the subgroup, and on the right, it is the reweighted performance of the model in the pseudo population. What we did is we just computed TA, which is the gap of the actual performance of the subgroup and the upweighted performance of V. If TA becomes 0, then the set of variables V effectively explains the gap successfully. It means that the difference in the model performance between subgroup is entirely caused by the differing distribution of V in these groups, not just the fact that the model is treating the two groups differently. If we control for V via reweighting, the performance gap disappears. We prove that a patient from subgroup A and a patient from subgroup B with exact same V, that is the breast density, will get the exact same prediction. Mathematically, R and Y is conditionally independent of A given V. In other words, we detected the reason of the systematic mistakes for the samples inside the subgroup A. So Clare detected these potential subgroup A's, and this method formally reasons why there is a mistake in the subgroup A. Now the question is how we can find these V's in a systematic way. We can do this either greedily, or we can borrow things from mutual information theory. So we copy all the results from the last slide. So here, if you remember, the prediction R and Y is conditionally independent of A given V. It makes this mutual information to be 0. And then we concentrate on Y equals to 1, that is only the positive patients, and denote the model error as E. So as E is a deterministic function of R, we can say that E is also conditionally independent of A given V. We can drop Y from here because we are only concentrating on Y equals to 1, that is the positive patients. it means that this particular mutual information is also 0. So here, this is the final loss term that we can use to learn V. We enforce these 3 constraints. The first term enforces this independence through the mutual information. The third term enforces the sparsity. And the second term enforces the overlap. So finally, where we are going? We are going towards an AI agent which will gonna consume the representation of the deep model. And the agent proposes some subgroups where the model makes systematic mistakes. This is the observation. And ultimately, the agent will gonna reason for the mistake. This will gonna complete my aim 3. This is my entire PhD timeline. And these are the set of papers that I co-authored and collaborated throughout my PhD. And finally, I thank my advisor and all my collaborators. A big thank you. And I wrap up my presentation and open up for questions.
So, go back to your first.
First aim.
Yes, first aim to the results.
Okay. Yeah.
Results.
This one?
Yeah, please explain like why force method is a little bit, result is a little bit worse than the black box.
It is less than the black box. So if you remember that we are distilling the knowledge from the black box. So the black box is actually the upper threshold. So that's why it is. So our goal is to not to compromise the performance of the black box and also increase the interpretability. So that's why it is a bit less, because the black box remains the upper threshold. We are distilling the knowledge from the black box. We are not training this model independently. Yes.
So, like you mentioned, you have a like relation that